Number 40. The force on a rectangular loop of wire in the magnetic field in figure 22.56 can be used to measure the field strength. The field is uniform and the plane of the loop is perpendicular to the field. Great, perpendicular. Letter A. What is the direction of the magnetic force on the loop? Okay, justify blah, blah, blah. So here's a picture. Okay, now really what they're asking for is they're really asking for what is the direction of the net magnetic force, okay, on the loop. And the reason for that is, and the reason why I'm making that distinction is because if you notice that this part of the wire is in a magnetic field that I just outlined, okay? So since the current here is downwards, the current here is to the right, and the current here is pointing up, the direction of the force changes for all three parts. So what we have to do is we have to look at each of the three parts independently and see what the direction of the force is, okay? So let's take into account this first little piece, okay? Let me highlight that instead, maybe that'll be a little better. So let's take into account this first piece where it's pointing down, okay? So remember, right-hand rule number 1, if you need a little help with that, check out number 1 of this chapter, and I think number 31. So the current here will be represented by the thumb. So the thumb is now pointing down. You got to point your thumb down. Your fingers then will represent the magnetic field. They have to be pointing out of the page or they should be trying to stick in the eye. So with your thumb pointing down and your fingers pointing at your face, right, keeping your hand in that rigid position where the thumb is 90 degrees relative to the fingers, your palm now should be facing, which will represent the force, it should be facing to the left. Okay, so that's the force on the green segment. Now let's take a look at the yellow segment here. Okay, pointing to the right. I don't really like the color in there. Let's do blue. Sure, not really much better. Anyway, pointing to the right. So now take your thumb. You got to point it to the right. Okay, your fingers then should be pointing out of the page. So they're trying to still stick in the eye. So this feels a little strange. If you like, my hand feels like my wrist is about to break, you're doing it right. So if your thumb is pointing now to the right and your fingers, your four fingers are pointing towards you, your palm should now be facing downward. So in other words, the direction of the force on that part is pointing down. Now, last but not least, let's take into account the last leg of this thing, okay, where the current is now pointing up. So point your thumb upwards, okay? With your thumb pointing upwards, right, you got to take your fingers now and point them towards you. And if you're like, wow, I thought my wrist was going to break last time, now it's really going to break because I can't even do this, then you're doing it right. The force now, your palm should be, in theory, if you can get your palm to do this, by the way, point directly with your hand flat and your fingers, your thumb at a 90-degree angle relative to your fingers, leave a comment, okay? Because I definitely can't. So, but the idea is that the force would be pointing here to the right. So, if you look at this in totality, if this current flowing through the green segment is the same as the current flowing through in the yellow segment, which, well, I think it should be because it's the same wire. What that means is that these forces would also be equal. And wait a minute, well, if they're equal but they're pointing in opposite directions, what happens to them? They go bye-bye, right? They cancel. So there's only one net force vector acting on this wire, and that is an unbalanced downward force, okay? Because there is no upward force. Imagine for a second, right, that you actually close this loop off, right? And you just kind of took this circle and you shifted it up. So the whole thing now was in the magnetic field, right? What do you think would happen? Well, you say the current's flowing now to the left, so your thumb is to the left, right? Your fingers are out of the page, so you're like a waitress or a waiter, and the force, your palm would be pointing up. So wait a minute, what would the net force be? Zippo, okay? Zippo. That'll be important for later. Anyway, net force here for letter A is down. Okay. Should I be dizzy from that explanation? I'm not sure. But maybe I should get out of this room and work out a little bit, huh? So letter B. If a current is 5 amps, if a current of 5 amps, is used, what is the force per Tesla on the 20 centimeter wide loop? So anytime you start talking about force, current, all this stuff, remember, you're going to be dealing with this formula that the force on a current carrying wire will be equal to now the magnitude of the current multiplied by the length of the current multiplied by the strength of the magnetic field multiplied by the angle between the magnetic field vector and the current. Okay, so I want to find not force but force per Tesla. So tell me which variable here has the unit of Tesla. You got to know your units, right? The magnetic field does. So basically what they're asking for is this. Divide out the B from both sides, and what you'll realize is that this represents force per Tesla. First of all, the units are Tesla. It's a little strange. They should have said, what is the Newton per meter, I guess, would be a little better. But you get the idea. This would be newtons per, excuse me. It would have been better to say newtons per Tesla, because Tesla is the unit, right, of magnetic field. All right? Anyway, you get the idea. This is what we're solving for. So F over B is now equal to the current. What do they tell you it is? It's 5 amps. What's the length? Well, it says, so it's the length that's experienced of the force, by the way. So you see how they say 20 centimeter wide? That's extremely important. 20 centimeter wide loop. That means that this length here is the 20 centimeters, as they also told you in the picture. Imagine they told you that all sides were equal, okay, and they told you that the total length of the loop was 20 centimeters, okay? The total length of the loop that's experiencing a force, at least, or that's in the magnetic field, is 20 centimeters. What would you do? Well, you'd have to then divide 20 by 3 to find this length, okay? Because these forces will cancel, so who cares? It's the net force I'm concerned about. Hopefully that makes sense. Anyway, you're going to take 5, you're going to multiply it by the length there of 20 centimeters, but you know we need that in meters, so do the conversion. Multiply them by the sine of the angle between. Now, what's the angle between the current and the magnetic field? Well, it's 90 degrees, right? How do we know that? Well, because your thumb is pointing to the right, and your fingers are pointing out of the page. So the only way to do that is if they're at 90 degrees. And blah, 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 blah. So you plug it into the calculator, but sine of 90 is 1. 5 times 0.2 is just simply 1. So this would be 1.00, I guess, newtons per Tesla. And that's then the value, okay? All right. I need a break. Guys, thanks for tuning in. Hopefully that helps. Please remember to help us out and subscribe if you can, and I'll see you soon. Take care.